Good afternoon, students. I hope you are well. So we will continue our chemistry classes, okay? And I hope you have studied the previous lessons. Please do not start this lesson without studying the previous lessons. So we will continue now lesson number 12 from chapter 20 from page 628. So let's start together, okay? Now, section 2, okay, voltaic cells. Okay, everyone? Now, the key terms, okay, what is of course a voltaic cell, a reduction potential, electrode potential, standard electrode potential, okay? Now, the voltaic cells use spontaneous oxidation reduction reactions, what? Okay, to convert chemical energy into electrical energy. Voltaic cells are also called galvanic cells. The most common application of voltaic cells is in batteries. Okay, so again, now why do we use the voltaic cells? Okay, it is a spontaneous oxidation reduction reaction. Why does this happen? To convert chemical energy into electrical energy, and most commonly it is used in batteries. Okay, everyone? So let's continue. The main idea here that batteries and fuel cells are two types of voltaic cells. Figure 2.1 shows an example of a voltaic cell, the ZnCu electrochemical cell discussed in the previous section. Okay, electrons give up at the anode, pass along the external connecting wire to the cathode. You see here, so figure 2.1, you see, yes, it's a big figure, but don't worry. We have taken examples like for this before, so you understand what is this, okay? You see here, this is an example of a voltaic cell. In a voltaic cell, electrons spontaneously flow from anode, you see this is the anode, to the cathode, okay? You see the electrons? The copper strip gains mass as copper ions become copper atoms. The zinc strip loses mass as the zinc atoms become zinc ions. Okay, everyone? So, the movement of electrons through the wire must be balanced by the movement of ions in the solution. Thus, in figure 2.1, sulfate ions in the CuSO4 solution can move through the barrier into the ZnSO4 solution. Okay, and this is the figure again. Please read it very well. Okay, everyone? And now, the dry cells pictured in figure 2.2 are common sources of electrical energy. You see, all of this is called dry cells, like the wet cell previously described. So this one is what? A wet cell. So you should remember, okay? So for example, if they tell you example on a wet cell, you should know this. Example on a dry cell, it's a battery, you should know. Okay? Like the wet cell previously described, dry cells are voltaic cells. The three most common types of dry cells are, okay, so you should remember the types of the dry cells are the zinc carbon battery, the alkaline battery, and the mercury battery. They differ in the substances being oxidized and reduced. Okay, so these are the types of batteries. Okay, now the zinc carbon dry cells, this one, you see, the zinc carbon dry cell. Now, batteries such as those used in flashlights are zinc carbon dry cells. These cells consist of a zinc container which serves as the anode, filled with a moist paste of MnO2, carbon black, NH4Cl, and ZnCl2, as illustrated in figure 2.3a, and we are going to see it. Okay, now, when the external circuit is closed, zinc atoms are oxidized, and you see this is the equation. So Zn, a pure element, so the oxidation number is 0, it gets oxidized, so loss of electrons, so it become, look, plus 2. From 0 to plus 2, the oxidation number has increased. Okay, electrons move across the circuit and re-enter the cell through the carbon rod. The carbon rod is the cathode or positive electrode. Here MnO2 is reduced. Okay, and this is the reduction, you see, from +4 to +3. So the oxidation number has decreased in a reduction. Okay, so you should know this. Now, and this is the figure 2.3a here, the zinc dry cell. You can see the carbon rod, the cathode, okay, and you can see what the zinc shell, okay, this one is the anode, okay, everyone? So you should know. Now, alkaline batteries, the second type, you see here, the alkaline batteries, this one, the second type, okay? The batteries found in a television remote or other small electronic device are frequently alkaline dry cells. These cells do not have a carbon rod cathode, as the zinc carbon cell. The absence of the carbon rod allows them to be smaller. Now, figure 2.3b shows a model of an alkaline battery. Okay, here you see figure 2.3b. See alkaline dry cell. Now, the cell uses a paste of Zn metal and potassium hydroxide instead of a solid metal anode. You see? So here, look. The half reaction of what? Look, from 0 to +2. So this is what? The half reaction of what? Okay, oxidation. You can see, look, the electrons. You see, loss of electrons. Okay, from Zn0 to Zn2 plus. Okay, the reduction half reaction, the reaction at the cathode is exactly the same as that for the zinc carbon dry cell. Okay, the reduction half reaction is similar to the zinc carbon dry cell, this one. Okay, this is the reduction. So here that's the oxidation, and this is similar, the reduction is similar to the previous dry cell. Okay, everyone? So, and here is the figure again. You can see the zinc dry cell and the alkaline dry cell. Okay, everyone? So what's the difference between the dry cells? The compounds or elements that are being oxidized or reduced. Okay, everyone? So this is the end of our lesson.